So thinking about removing from the binary search tree is really pretty tricky. Now, a lot of the time, it's pretty easy. It's easy when you're removing a leaf. So let me build a simple tree here. Wait a minute. Wait a minute. I missed something. There we go. All right, so we have this nice, perfectly balanced binary search tree. A pity if anything should happen to it. Removing a leaf is very, very easy, right? So if I need to remove A, C, E, or G, I search my tree for the value I want to remove. When I find it, I have to check how many children does it have. And if it has no children, bammo, the parent becomes a null, or the left child of the parent becomes a null, and A goes away. So that's very simple. There's another case which is fairly simple, a little bit more involved, which looks like this. So if I want to remove G, I search through my tree, and I find that G has one child. So what I can do is I can say F's child is now H. So I can just bypass my G, and it's gone. That's very, very easy. Notice that this situation is almost precisely the same as removing a value from a singly linked list, right? It takes, learning to remove from a singly linked list was certainly a little tricky, but not fundamentally difficult. It's still fairly straightforward to think about. You're just bypassing that link. And when you bypass that link, of course, this reference goes away. And ultimately, in the context of a language such as Java or Python, G ultimately gets claimed by the garbage collector because there are no references pointing to it. So, for our purposes, it's gone. My diagram is not as pretty as it was, but we still have a nicely balanced tree. So the really tricky situation is something like delete D. Well, the finding part is easy. It's like, okay, well, I found D, but then the question is, well, what do I put there? And so there are two ways to do this that I think both groups had a chance to kind of play with and encounter that in the end are kind of straightforward, but there's some subtlety here. So the key concept, and this is something that I went over last time, is the idea of predecessor of a value and successor of a value. That is, given some value, we can easily find its predecessor or successor. Given that the value is a root node with two children, it's actually even easier. That is, we can say that, the predecessor of a root, and we know we're dealing with a value that's got two children because the 0 children just snip off, the 1 child we do our singly linked list delete, right? So we're dealing with two children. So the predecessor is just the maximum of its left child. And we also talked about the maximum last time on Friday, right? How do we find the maximum of a binary search tree? The maximum. We go all the way to the right. So if I'm removing D, its predecessor is the maximum of its left subtree. That is, I go all the way to the right on the left. So its predecessor is C. Similarly, I can think about the successor of the root, and that's going to be the minimum of the right subtree. So the minimum of the right subtree. So how do I find the minimum? I go all the way to the left. So if I find the minimum of the left subtree, I get E in this case. So here then is a general way we can think about it. There's a symmetry here. You can really take either approach. To delete where there's a case of two children, what you can do is just copy either the predecessor or the successor. It doesn't matter which. Then remove whichever of these you chose from its subtree. So if we think about this situation, I'm removing D. So to remove D, I copy E to the root. I then tell my right subtree, remove E. Now, the beauty of this is that the predecessor or successor has no more than one child. If the predecessor or successor had two children, then let's think about the successor. If the successor had two children, its left child would be the actual successor. So that was an extremely hand-wavy proof by contradiction. But I think the logic is very clear.
So, question, could we call recursion in this case to
Yeah.
to
Recursion is precisely what I'm recommending.
so in this case you would call successor root, and then min right, then min left.
I would just tell the right subtree, remove that value. And I know that within that remove, it'll boil down to either being a leaf or a node with one child. And those removes, as we saw, were very, very easy. And that's removing from a binary search tree. Is it super easy to code? Well, not exactly, right? There are going to be some subtleties here. But I think we see what all the basic ingredients are. If we can find a minimum or a maximum, and if we can remove a leaf or an interior node with only one child, then dealing with the two-child case is just a matter of finding either the minimum of the right tree or the maximum of the left. It really doesn't matter which. So in your code, you're just going to arbitrarily pick one. And that's okay. And once you've done that, it goes through and it's been simplified now to the easy case. And so note that this approach avoids a hazard that we saw in some of our card games, which is if I simply swapped my D down here, it's now no longer a binary search tree, which is bad. So what we do is we actually leave this value alone, and then we just say, oh, I want to remove it. And then poof, it's gone.
So pop that. You could pop it basically.
Well, not really, because this isn't a stack.
Oh wait, we'll poof it or whatever.
Yeah. Yeah. So that's removal in a nutshell. Any questions about that? So now we're going to get to the really hard stuff, which is dealing with a tree that's not balanced. So in order to get the good properties in terms of time efficiency on a binary search tree of log n height, sometimes we may have to rearrange things. So here's an example where we might have to rearrange things. let's say I insert A, and then I insert B, and now I insert C. So this is not going to end well, right? My binary search tree is going to become a binary search singly linked list very, very quickly. But if you look at it, you might think, it doesn't really have to be this way. What I mean by it doesn't have to be this way. This specific set of elements can be realized by multiple equivalent binary search trees. Here's another one. Imagine I inserted C first. Then I would have C, and then I put in B, and then I have A. So notice that these are both equivalent binary search trees. Of course, the one I really want is this one, B, then A, then C, or even B, then C, then A. So what I want is to have some way to transform either of these into this specimen of tree beauty. And the way that we do this is by using what is called a tree rotation. So I'm going to begin by showing you the general forms for a tree rotation, and then we'll talk a bit about how those general forms are realized in practice. So the way to think about the general form is that you've got the nodes that are going to move, but then associated with each of these nodes are subtrees. And following a convention from a long-lost textbook, it's actually not long-lost, but what have you, we're going to designate the subtrees with Greek letters. So we'll call that subtree alpha, that subtree beta, and that subtree is gamma. So the key to tree rotation is to recognize that these two general patterns correspond to the same search tree ordering. I can move B to the root and make A its left child. When I do this, A retains alpha as a subtree. B as a left subtree. B retains gamma as a right subtree. But here's the tricky part, is this beta subtree that was the left tree of B can no longer be the left subtree of B because A has become its new subtree. The key insight is that the left subtree of B can validly become the right subtree of A without violating our in-order traversal and our search tree ordering. If you think about an in-order traversal of either of these, to begin with, in an in-order traversal, you visit the left. And so the first thing visited will be alpha. It then backs up to its parent. The parent of alpha is A. Now, let's imagine the left side. We go to B, but we must first visit its left subchild. So we get beta, then we get B, and then finally we get gamma. Now let's think about the right version. You start at alpha, you visit its parent A. Now, from A you proceed to the right subtree, which is beta. And now you have to backtrack up to B, and then you visit gamma. So in terms of an in-order traversal, these two arrangements of the tree are equivalent to each other. So if I did these backwards, that's okay. I am going to unbackward them. This will just take a second. Okay. A alpha, beta, B, and gamma. A, B, alpha, beta, gamma. There, that's better. If we go in this direction, that is called a right rotation. So the reason I had it backwards is that when we think about the idea of the right rotation, B is getting rotated down to the right. If we go in this direction, it is called a left rotation. A is getting moved down to the left. Now, thinking about the tree as a whole, do these rotations depend, in terms of how many operations they perform, on the size of the tree? So if I've got big subtrees, does this become slower than if I have small subtrees? Why not, Caleb?
Because you're just pointing to the subtrees. You're just changing the parents of the subtrees. You're not changing everything about the subtrees.
That's exactly right.
But if you have no subtrees, then it would be.
Well, in practice, what implementations of binary search trees do that involve rotations is to have sentinel nodes at the leaves. So, because it simplifies the rotation. So they'll typically have just little dummy nodes at the fringes, just to, because yeah, if it doesn't have any children, then the nulls get annoying pretty quickly. But that's easily solved. It's easily solved. So that's right. A single tree rotation is constant time, right? That constant specifically is that we are changing several pointers. So the parent pointers of A or B are going to have to be changed. And the subtree pointers for whoever is becoming the new parent and then moving beta around will have to be changed. So we're looking at like 3 pointer changes, which isn't too bad. It's a nice small constant. In practice, there are a couple of ways we can deal with an extremely irritating issue of parent pointers. One way to deal with it is to have bidirectional links in the search tree. Another way to deal with it is to have the parent make some kind of recursive call to rebalance the child, and then it always changes its subtree node to be whatever gets returned from the recursive call. I personally find that approach easier to implement. Because then you don't have to have the pointers going both ways, and playing with links that go both directions is really, really tricky and bug prone. So, having shown that rotations are a valid consideration, we can look here and see if somehow we know that the tree is out of balance, what we can do is use rotations to balance it. So that seems straightforward, except that we have to have some kind of an accounting scheme to determine whether or not the tree is in balance. For the lab this week, you'll be implementing binary search trees and you'll implement rotations. I am not going to have you implement the accounting scheme for balancing. Especially once you start doing removes, the accounting schemes get pathologically irritating to deal with.
So we're not going to be fighting with it.
Right. But what I am going to do is outline maybe what's arguably the best known of such schemes. And this scheme is known as a red-black tree. So what are the rules? This is kind of like a heap. It's got a bunch of rules. And when the rules get violated, the repairs are what's essential for ensuring our good time complexity. So all nodes are red or black. All red nodes have black children. So an interesting corollary of this is that so red-black trees usually use sentinel nodes for the leaves, and the sentinels are all black. So you can have a red node, which is technically a leaf, but it really has these dummy nodes, which are black children. And the black height on both sides is the same. So if you take a path from the root to any leaf, you'll encounter the same number of black nodes, no matter what. So those are the essential properties of a red-black tree. So then the question arises, well, how can you use this as an accounting scheme? The absolutely crucial thing that we do with the red-black tree is to say that all new nodes are red. Then, if you wind up having two red nodes in a row, you perform tree rotations to flip everything around. And in doing so, you wind up coloring things black, and it makes things work beautifully. Now, the key to this working is the idea that the black height on both sides is the same, in combination with all red nodes having black children. So what emerges from this is the fact that you can't have more than twice as many nodes in a bad path, that is, a path that contains red nodes, as compared to a good path, a path that's all black. Since two red nodes aren't allowed together in a row. So the essence of the scheme then is something like the following. Let's say you've got a red node and you insert another red node next to it. If you insert that red node on the right, then you can perform a left rotation to rebalance your tree. So let's think about why this works. So I've got my two little sentinel nodes here. So this one's red, this one's red. I've got my black sentinel nodes. And I know that over here, I've got something black, which if you go on down, is a totally legitimate red-black tree. So let's think about the implications of a rotation.
There's the question of
that's what we're dealing with right now. Okay, so now we perform this tree rotation, and the key to the success of the tree rotation is the idea that once we've done the rotation, we get to color the rotated node black. So if you think about the fact that we had a legit red-black tree over here, so this has to be a black node. Once we perform this rotation, this new parent becomes black. And the black and the red node here doesn't interfere with the black heights being balanced on both sides. Once you do this, however, or actually, I think it was the other way. Yeah, it was definitely the other way. And the reason is that one becomes black, that one becomes red, and then you recursively go backward up and see that I now put two red nodes together. And so as you go on up, you might wind up doing a lot of rebalancings, but you're still only doing log base 2n rotations on the way up, knowing that the rotations themselves are constant time. So red-black trees are fairly tricky to implement. It's a pretty non-trivial project. It's a lot of fun to do. It's interesting. We've decided that a full-blown implementation of a full-blown red-black tree isn't our best use of time in this course. Like, you'd certainly be welcome to play with it as a project or whatever. But in the end, it's a lot of closely follow the published pseudocode of the algorithm until everything lines up exactly according to it for all 8 special cases. I mean, I've certainly implemented them. It's interesting to do, but I think it's a little more interesting to see several different ways of achieving this goal of a data structure that maintains the sorted ordering. So last week we saw the skip list. This week we're seeing the binary search tree. You'll play with the rotation idea, and I'm going to have you personally balance your own trees. And then next week, we're going to look at yet another variant of a tree, which is called a trie, which represents a different approach to keeping things balanced. And for strings as keys in particular, it's actually a lot more efficient than a binary search tree while maintaining a sorted ordering. And so we're going to look at the trie in a lot of detail next week. The following week, we're going to look at kind of the ultimate dictionary implementation, the hash table. And that'll actually be our last lab. After, I think the final week of classes, the lab is simply work on your final project. So we have 3 labs to go. We've got tomorrow, which is the 5th. We've got the 12th and the 19th. And then we'll have kind of a day of just projecting. Yes, Jane?
Are we going to have a lab the week of Thanksgiving?
Oh, goodness, no.
Okay.
Yeah. Yeah, there will not be lab that week. So, yeah, so if you need to leave at noon on Tuesday, leave at noon on Tuesday.